Okay, we're going to talk about electric power in a circuit with a resistive element. Now, this thing broke. So let's suppose we have a battery, and we have, it could be like a light bulb kind of a thing, like a Christmas tree light. So you get a little electric cell and hook up the wires up to it, and it will, here's like a little Christmas tree light or something, and it will give off light, right? And so obviously we're consuming energy here. There's energy stored in the battery. The battery boosts the voltage of the charge moving through the wire. We do have a current, and now it is going to jump down in voltage back to zero, and in doing so it gives up its energy. The electrons have energy up here. They don't have any more energy down here. They give all their energy to the light bulb, and the light bulb uses that energy to make light and heat. It doesn't have to be a light bulb, though. This could be a motor. It could be a speaker. Anything that uses energy and makes changes in the environment in some way, light, heat, sound, turning a propeller, a motor, whatever. And so anything that takes the energy out of electricity, we call that a resistive element or a resistor. Now, we talked about resistance last time as if it was just the resistance that comes from current flowing through a metal. But we can think of resistance as being the voltage we need to get a certain amount of current to flow. And this is how I want you to think about resistance. If you have a motor that's going to, like a DC motor that's going to spin, that motor says, hey, you know what? If you're going to get an amp of current to flow through me, you've got to deliver X number of volts. That's what an ohm is. Like if this was had a resistance of 20 ohms, that means it would take 20 volts to get 1 amp of current to flow through it. So in other words, it resists current. It says, hey, you got to have lots of voltage to get current flow. Now, if it has low resistance, like 0.01 ohms, that means you need very little resistance. Very little voltage to get the current to flow. Now, it's kind of difficult to draw light bulbs and motors and speakers or anything like that. So we have a symbol for anything that takes the energy out of the electricity as it flows, and that's this zigzaggy symbol like this. And this is the symbol for a resistor. Now in the next chapter we're going to use the symbol a lot, and so I think it's useful right now to kind of review our symbols. We have, am I still on screen? Yeah, we have the symbol for a battery of cells. Okay, so this is a battery. Then we have a symbol for, like this is a capacitor. And now we have a zigzaggy thing, which means a resistor. Now, if you break open any electronic device, you'll find these little resistors in there. They kind of physically would look something like this. They look like little tiny sausages with wires on them. And then they have stripes. And these stripes, if you know the code, the different colored stripes, you can figure out what the resistance is of that resistor and what the tolerance is and that sort of thing. But and they do what they do is they help a circuit designer control the current that flows through that. Now, and these three circuit elements that we're dealing with here, they do different things when you think about energy. The battery delivers energy to the circuit. Okay, the battery has chemicals in it that will undergo some kind of chemical change and will boost the voltage or the joules per coulomb of charge that flows through it. So it boosts the energy value of the electricity in it. Now, capacitors. Capacitors store energy. You create an electric field between the plates, and so the current will eventually stop flowing through it once it's full of, has its maximum charge for the given voltage. But that energy is there waiting to be used in the circuit later on. Now, a resistor removes energy from the circuit, and it hopefully does something useful. But sometimes all resistors do is heat up the circuit because you're actually using it to control how much voltage and current is delivered in the rest of the circuit. In which case, all it does is give off heat. Okay, and this is why your laptop gets hot. All right, if you're using a laptop and it's been on for a long time, here's my laptop, okay, and I feel the bottom of it, and it's all nice and toasty warm. Feels good on my hands. Okay, well, that's because these resistors are removing. There's lots of little resistors in there, and they remove a little bit of the energy from the electricity. Also, all wires have a little tiny bit of resistance, and so they give off heat. In fact, it's managing the heat given off by wires that have current running through them that is the big challenge when designing computer circuits. I mean, these things are getting so tiny, and yet we're trying to shove current through them, and they're getting so hot that they can melt, or they can, damage themselves. And so some of the first supercomputers in the 1990s, there was this computer built by a company called Cray, and they would build supercomputers, which probably aren't much better than your desktop at home now. But at the time, they were awesome. And they actually had the CPU of the computer immersed in liquid nitrogen to keep it cool so that the circuit wouldn't fry itself. Now, since then, they've managed to do the same computation with much less current, much less power, and therefore it doesn't get nearly as hot. But in any case, I just want you to see right away that batteries deliver energy, capacitors store energy in the electric field, resistors dissipate or use the energy and extract it from the circuit. Okay. Now, if you want to know at what rate the energy is being, is being used by this light bulb, and its resistance, it's actually pretty easy to figure out how much energy is leaving. Let's say, let me redraw this. Let's say I've got here's my switch. That was our other symbol, but I didn't list it. And here's my resistor. So, and here's my voltage from my battery. Now, let's say I close this switch, and now current is going to run through. Well, current is I is measured in blank number of coulombs of charge that go by every second. Okay, so there's going to be a batch. Let's say the current is 2 amps. That means 2 coulombs of charge are going to move through this resistor every second. Okay, and then. But now take a look at this in terms of voltage, man. Let's say this was a 12-volt battery, okay, and let's say this was, and this was delivering 2 coulombs per second. Well, can I figure out what the resistance is here? First of all, what is the resistance here? Well, if 12 volt, well, first of all, what's the voltage drop across the resistor? What does it have to be? It has to be 12 volts, because a voltage man will start his intrepid walk around the circuit here, and he starts off with 0 energy, walks through, boom, gets boosted up by the battery. Oh, now we got 0 volts. I'm sorry, now we have 12 volts. So we got 12 volts up here, 12 volts up here, 12 volts up here, 12 volts up here. Now I'm going to jump down here, and I'm going to throw my energy away. Now in a capacitor, I would store the energy, but in here I release it into the world, doing something, work or light or sound, and then now I'm back to 0. So it has to be a 12 volt drop. But so well, we said that resistance, right, is equal to delta V over I. And so yeah, I can figure out what the, see, it's 12 volts divided by 2 amps. And so that's 6 volts per amp. And of course, a volt per amp is called a what? Okay, I want you to just meditate on this for a while. It's called an ohm. Right? See what I did there? Okay, it wasn't appreciated, but okay. Okay, no, I wanted this not applause, it's laughter. All right, so there's my resistance, but I want you to think about this in terms of energy. If I've got 2 coulombs pushed through this resistor every second, and those, and each, well, what is a volt? It's a joule per coulomb. So it's telling you every coulomb of charge that moves through here is going to deliver 12 joules of energy. It's going to give up 12 joules of energy. Well, what happens if I multiply how many charges are moving by per second by how much energy each one of those charges delivers? I'm going to get power. Watch. If I take 2 coulombs every second is flowing through this circuit, and each one of those coulombs delivers 12 joules. I get 12 joules per coulomb. Well, that's telling me how many joules per second is being given off or is being delivered to that resistor, that battery, or that light bulb, or that speaker, or whatever. It's 24 joules every second, or 24 watts. So what we're going to just say is, hey, power is equal to the current that runs through the circuit divided or times the voltage. Now this equation, you express it this way. You can kind of think of this as being the power delivered by the battery. Let me redraw the circuit again. See, this is the power. Here's the current. Well, this is my voltage. This is my resistance, and here's my current. You know, moving around the circuit like this. Well, this is the voltage. You can think of this as being the voltage delivered by the battery. Or you can think of it as the voltage delivered to the resistor. It's the same thing. But we also know that R is equal to V over I. Now this is Ohm's law, and we usually don't write it this way. I like to think of this as the definition for resistance. R equals V over I, but we usually don't write it that way. We usually write it as voltage equals IR, just because it's easier to write down. And this is what we call Ohm's law right here. Well, if V equals IR, I can substitute this in here. And so I get a different power equation. It's equal to I times IR, or power equals I squared R. And this gives me a value for the power being delivered to this resistor depending on its resistance and the current flowing through it. Now, of course, I can solve this equation here for I. I can say, oh, current is equal to voltage divided by resistance. And then I can take that and plug it in up here. And when I do, I get power equals the current, which is V over R, times V. And so I get another power equation. Oh, I'm off screen, huh? Not quite. V times V is V squared. So power is equal to the voltage squared divided by the resistance. So the way I got this was just using Ohm's law. So let's summarize. The power delivered by a battery to a circuit, or the power used by that circuit, is equal to I times V. And if the current is flowing through a resistor, the power will be equal to I squared R. And if you want to think of it in terms of voltage, the voltage drop across that resistor is V squared over R. So this is our power equation for direct current circuits with resistors. So it's pretty easy if you understand this. Now, there is one thing that you should be aware of, that in electricity we have very weird units for energy, the energy you use when you're using electricity. And I think we talked about this before in mechanics, but we'll just review it briefly. We also know that power is the rate at which I use energy. So I'll say energy over time. Well, so energy is equal to power times time. Anytime you multiply power times time, you've got a unit of energy. Okay. Well, in electricity, it's quite often the case that we will use like the energy used, and you can call that delta U or E or whatever. But the units we use for power are quite often kilowatts, and the time we express are hours, a kilowatt hour. It's a weird unit of energy. I don't like it, but it's what PG&E uses, or Edison, all the utilities and so on. They measure energy with kilowatt hours. Now, you can easily change kilowatts to watts and hours to seconds and end up with joules. But your number is going to be really, really big, chances are, if you're talking about the kind of energy you use in your household. Well, what I don't understand is why they don't just use megajoules. You know, we megajoules and kilowatt hours are about the same order of magnitude. So instead of, spending charging you 30 cents per kilowatt hour for electricity, they could charge you, 12 cents per megajoule or something like that. But they don't. They didn't ask me. So, all right. So anyway, just to summarize, let me zoom all the way out. Remember that electric power is just how much energy per unit time, joules per second, energy is leaving the circuit. Okay, batteries deliver energy to the circuit, capacitors store energy, and resistors dissipate or use the energy. It removes the energy from the circuit. Okay, and if you, it's kind of obvious, if you multiply the current times the voltage, that's a measure of the rate at which energy is leaving, or delivered to the circuit and leaving the circuit. It's kind of conservation of energy. Okay, so that is all. Are there any questions? What's that?
I think this is the one assignment I've sat through and been like, I think I can do
Yeah, yeah. But you guys, you know,